So we're looking at lecture 2, and we look at some LLM motivation and history of LLMs. So the course outline, right, I think we spoke about this last time, consists of 4 different modules. The first is building the foundations and prerequisites. We spend a little bit more time here, and this might be familiar for you. And for some of you, we might be going slow, okay? The course might be slow. For some of you, it might be just right. But then once we finish this, we'll really accelerate and the course picks up. So it's just like this, it's going to be like a quadratic curve almost. It's going to be slow initially and then it picks up really quickly. So just be patient if you're like, okay, this is something I already know, because what you don't know will come up very soon. So that's building the foundations. And also if you do know stuff, it's good to like refresh it in a deeper way, understand it in a deeper way. So that's the goal of the first module. This will be about 3 or 4 lectures, including today. So the first 4 lectures of the whole course will be on the foundations. Then we go into transformers and we discuss different aspects of it, including the architecture, the discriminator one, the generator one. And I think before that, we'll also set context with embeddings, because embeddings is a very popular concept that shows up in different places and very, very useful as a practical tool that you can use in the industry, right? And then we'll also look at applications. The third component focuses more on the generative AI aspect, which is the a generative transformer. So we look at GPT 2, 3, and also GPT 3.5, 4, and 5. And we look at agentic framework, prompt engineering, fine-tuning and evaluating LLMs, and open source versus closed source LLMs. Okay. And then the fourth one is like a mix of topics. So we spoke about this. There'll be some vision models we'll cover. There'll be some small language models we cover. And we also cover responsible AI. Okay. So hopefully everyone's taken a look at the course webpage. The lecture notes before the class are uploaded to the webpage, and also after, if you do any annotations, are uploaded there as well. If we have a recording for a class, I think we do have recording for almost every class. We'll upload the recording as well, so you can also refer to it after class. The recording will be uploaded in a day or 2, so there'll be a little bit of a lag, 1 or 2 days. The assignment link is linked at the bottom of the homepage of the course. It's on Canvas, so if you know where Canvas is, just go there. If not, you can just find the link on the main page as well. Okay, so we spoke about what I would like you to take away last time. We're going to cover a mix of concepts, implementation, and also ideas. So how many of us have let me ask this, how many of us have not set up Discord yet? Okay, 1 of you. How many of us have set up Discord? See, some people are not raising hands for both. So I don't know which category to put you in. Maybe the category of not having set up, but you're too shy to share. So do set up your Discord, because all the messages will be coming in there. Okay. And so, yeah, I think on Discord we have the general channel, and then we'll also have an assignments channel. And I just created a lectures channel, so you can also see there's a lecture, any lecture note updates or anything related to lectures will post on the lectures channel. So just check one of these channels. And there's something I mentioned last time. If you find any interesting article on LLM that you'd like fellow students to read, just share it on the group. It's your group, so it's just a way to get you started, to start sharing your thoughts and ideas. Okay. Okay, assignments. This is something we didn't cover specifically last time. So let's look at the breakdown of the assignments and the grading for this course, right? So it's a mix of different things. We'll have in-class exercises. So that's the first component. That's 15% of your grade. So every class, there'll be an in-class exercise. Almost every class. We didn't have one last time. We might have one today. And we'll have a poll or a form for you to submit the responses in class. If for some reason you couldn't access it or you were away for the day, you'll have until the end of the day to submit your responses. And as long as you make a submission, it'll keep adding to your grade, right, towards the 15%. this is where we cover the concepts. So the conceptual component of the course will be through multiple choice questions. So you have different choices and you can pick between different choices and test your concepts, okay? And don't use an LLM for it. Although this is an LLM course, we encourage you to use your own intelligence to answer for anything, right? So the next one is coding assignments. So we'll have 2 coding assignments. The first one is assigned as of today, I believe, or it's not. Is it assigned? It's assigned. Okay. So the first one is assigned. The TA told me that it took her 4 hours. It might take you anywhere between 4 hours to 10 hours. It just depends on how much time you need to set up and stuff. So it'll be due next Tuesday. So we'll have 1 week for the first 2 coding assignments. Definitely get a head start on it. Don't keep it to the last minute, because there are some, there is a question on training a PyTorch model, and if you're new to it, it might take some time, okay? After the first 2 coding assignments are done, we then move on to mini projects. So we'll have 3 mini projects. These are very hands-on, very immersive. They're more than a regular coding assignment. The focus is on depth and intuition and a demoable component. There'll be something that you can demo, like a web app or a web page or a Kaggle competition, right? Where you can actually, how many of us have done Kaggle competitions in past courses or projects? Kaggle? 1, 2, a few? Okay. If not, you'll get to experience that. So there'll be a leaderboard of all the teams in this class, and you can see how you can rank against each other, just as a friendly competition, but also to know if you're way off or you're on target, right? So, and the Kaggle contest is usually measured through some metric like accuracy or precision or recall or whatever, right? So yeah, I think you'll get 2 weeks for every mini project, so 15% per project, roughly, and they can get pretty intensive. Like you'll have to spend a significant amount of time, but you also learn a lot. And the good thing about mini projects is, because you spend so much time and you go into depth, it's also a good thing to add to your resume, right? Resume is not like, okay, I checked off this course or checked off that course, right? It's not that deep if you just mention courses, but if you mention some projects, it adds a bullet point on your resume. So this can be a little bit of that. And then we come to project presentation. This is connected to the mini project. We'll have a project presentation. I've currently put 15% as the grade for this, but it might be 15 or 10%, we'll see. So in the finals week, on a Monday or Wednesday, every team will get to present for a few minutes on a mini project that you worked on. So one of the 3 mini projects you can present, and there'll be questions, and you'll be graded on how you present and how well you understand or your insights and results. So it's also a way to showcase what you've done in front of the class, okay? So this is the 7 minutes per team plus 3-minute questions is based on a previous course. Since we have a lot of people, we might actually compress it to 5 minutes plus 2 or something like that. We'll see. So that's the 4th component, okay? The 5th one is the paper presentation. So last class we mentioned that you will get to pick a technical paper, like a peer-reviewed paper that you can actually read and present in class. So starting 3rd week of this quarter, so not this week, but 2 weeks from now, the last 15 minutes of class will have 3 presentations every week. So each team will get about 3 minutes to present plus 1 or 2 minutes of questions. So that's about 5 minutes per team. And you'll have to, so we'll form teams and everything. So don't worry about it, we'll form teams. You'll work in teams of 2. And you'll have to record your 3-minute video, because what you've seen in presentations like this is people go overboard, or it's, you're running short on time and then the whole thing drags. Also, your quality is higher when you record, because you're going to try and see how it looks and you iterate and everything. So you'll actually record your video before class and we'll watch it in class, and you'll be there to answer questions from TAs or instructors or students as well. Does it sound good? So this will, you can pick a paper. So we have about 95 students, about 50 teams. We'll have about 60 or 70 hand-picked papers for you to pick from. So you can, if you pick sooner, then you get to pick that paper. Otherwise, you have to go with whatever is left. If you really want to present some other paper that's not on the list, you can let us know, and then if it sounds suitable, you can go with it. The other thing I want to mention was that so there'll also be a schedule to it, right? So again, schedule is first come first serve because there's limited slots. If you go to the spreadsheet and then you pick a slot, that's yours. But if you wait, you might get a really early slot, like in 3 weeks, in 2 weeks. You might be the first one to present. So be okay with that as well. Okay. Either way, we'll release the papers in this week, maybe in the next 2 days. We're still finalizing the list. So even if you're the first to present, you'll have a week to prep for it. Okay. Does this sound good? So this is to, yeah.
So the mini project as well, that's not team oriented, it's just like the project presentation becoming a team to present?
The mini project is also team oriented. Yeah, so mini projects are team oriented. Paper presentation is team oriented. Coding assignments are individual. Okay. So teams of 2. So we don't encourage teams of 3 because it's hard to split work, and one person may contribute more than the other. So teams of 2 is good. If you're an odd person, if there's an odd number of people, we'll figure out something. Does it sound good?
And we form our own teams?
Yeah, you can form your own teams. So every class will do some interaction, and we'll ask you to sit with random people, so you'll get to know people as well. So you can pick and choose people you want to work with. Okay. Someone asked, I think sometime back, if you pick a team for the paper, is it the same team for mini project? You can switch teams. You don't have to be stuck with one person. But if you do want to work with one person, you can work with that person as well, whatever makes sense. Okay, does it sound good? So the assignments kind of reflect the kind of outcomes that we want for this course. So we wanted conceptual understanding, that's in-class exercise. We wanted hands-on coding experience and ability to work with APIs, so that's coding exercise and mini projects. We want to be able to demo, that's mini projects. And we want to be able to go deeper. You can read a bunch of articles posted by someone that's very high level, and you can get a reasonable high level understanding, right? But once you want to go a little bit deeper, you cannot avoid reading technical papers. So that's the last component, is paper reading and presentation gives you depth, or it forces you to deal with depth, right? While you might just want to skim the paper, while reading the paper, you actually appreciate and understand or go deeper into the nuances of the paper, okay? And gives you confidence to actually read papers on your own if you have not done it before. Okay? Any questions on the assignments? Okay, moving on. So assignment 1 is assigned today, due next Tuesday. Focus on collab, APIs, and LLM discovery and insights, right? So yeah, we spoke about assignment flow as well. Okay, course flow. Like we said, like I said earlier, the first 2-3 weeks will be a little bit slower, taking our time, building the foundations. But after that, we're going to go, you'll see it becomes progressively, when you get to transformers, it can get pretty complicated and intense. But hopefully you have the foundations and you can go with it. Okay. And also we're going to jump back and forth between business applications and concepts and theory and coding. So we're going to circle around different things. So that's also part of the course flow. Okay. So let's talk about engine versus API. So engines are different from APIs, and we shouldn't confuse the two. Like BERT and Llama are engines or foundation models, whereas ChatGPT 4.0 or ChatGPT 5.2 is an API, and it adds layers on top of a foundation or an engine. So you can actually use it for your end applications, right? So some examples of engines, you have BERT, and there are different versions of BERT, Roberta, Distal BERT, and so many different tiny BERT, which is purely an encoding transformer, right? And then we have GPT, which is actually a decoding transformer. So GPT, the original paper was from Google. Some of the authors are from Google, but then OpenAI took it from the open source and made it into ChatGPT, right? And then we have Claude, and we have, let's say, Stable Diffusion. These are like engines or foundation models. And then when you look at the APIs, so BERT, you'll actually use it if, in terms of API, you don't really, use it as an API, use it as a PyTorch model, essentially. Typically, you load it as a PyTorch model. For GPT, you have like GPT-4, 4.0, 5.2, or the thinking version, which takes much longer to get a response, but might have more reasoning. And then we have Claude, which is the engine, and then you have Opus 4.5 or Sonnet 4.5 that are the end APIs that you can use. Then you also have Llama 3 model, and then you have the Instruct fine-tuned version of that. Let me just make sure this is minimized. Okay. Actually, let me just pin myself. And okay. So we have Llama 3.2, and then we have the Instruct fine-tuned version. So for example, if I went to Llama, on Hugging Face, if I went to Llama 3 and checked out Llama 3, Meta Llama 3, then I see the under Meta Llama, we have Llama 3.21 billion, Llama 3.2 3 billion. We also have a Llama 3.2 1 billion Instruct. So the Instruct version is fine-tuned for taking instructions, whereas if you use the 3 billion version, the non-Instruct version, it'll still respond, but it will not be polished, and you'll wonder if something went wrong in the language, because it's not fine-tuned to take instructions and respond. It might give you generic responses, or it might not be as polished as an Instruct fine-tuned version. So, so we have both. And then for Stable Diffusion, for example, that's the engine, the foundation, and then you can also say pre-trained models. They're the pre-trained version. And then we have Midjourney or DALL-E or other ones, Sora, that's come out recently as well as APIs. So we'll touch upon vision a bit towards the end of the class. And this is also where we'll touch upon multimodal. But for the most part, we're going to focus on language in this class. Okay, yeah, so this is large vision model, pre-trained model, foundation model. So again, you can use interchangeably. Foundation model, pre-trained model refers to the base. What's your base? What's your foundation on which you add other layers of instruction, reinforcement learning, other fine-tuning and stuff. And then the pre-trained model or foundation model for large language models are these, right? Yeah, another way to think of API as far as LLMs or generative AI models are concerned is a foundation model plus a bunch of extra fine-tuning plus some extra hacks and plus some responsible AI plus some other filters, and then you have like the end API that you actually use, right? So the
say that the foundation model is basically the base. Think of it a car analogy, like it's the engine, but you take it, you put extra carburetor and stuff on it.
Yeah.
A racing engine.
Yeah.
And then you put extra electronics and stuff, then you call it an API.
That's right. That's exactly right. That analogy is perfect. So Yeah, I mean, you're saying it's not a fancy engine, it's a fancy car, right? But it's the same analogy. It's like you have a foundation and then you build on top of it. But you actually fine tune the engine as well. So it's not just adding cosmetics. So the
change certain parts of it to make it to change its code and stuff.
no, you change a lot of it, lots of it, all of it actually.
Oh.
You change all of it because the pre-trained model is trained on a certain set of. We'll come to this when we get to pre-trained models and fine-tuned models. The pre-trained model is trained on a certain set of corpus of data, which is like millions and millions of documents from the mined from the web. But it's not fine-tuned for instructions. So you change all of the model parameters when you fine-tune. And when you change all of the model parameters again when you do reinforcement learning. So it's not a small change. It's actually a heavy change. It's just that it takes less time. It might take a month or 2 months with tons of GPUs. You might use like 800 GPUs, and then you, in 2 months, or I mean, the time is reducing now, but 1 month or 2 months, you have a foundation model, and only a few companies can actually afford the cost. It's a 2-month job, you get a $2 million bill, so every time you do it, and then, so only a few companies can do that. So that's the foundation model. But once you've done that, you might use a smaller corpus of data set to do the fine tuning and for instruction and for reinforcement learning. So, but that's still very important. It's a very important fine tuning. And as far as parameters is concerned, everything changes. Okay. Even something as simple as LoRa fine tuning. How many of us have heard of LoRa? LoRa, a few people. Okay. So LoRa fine tuning is like one of the easiest and most efficient ways of tweaking this foundation or instruct model. So you don't tweak the foundation model, you tweak the instruct fine-tune model. So you already tweak a fine-tune model. So it's a fine-tuning on a fine-tuning. And you can specialize it for specific business tasks, right? So even LoRa changes every single parameter, right? Although it's a low-ranked thing. So anyway, we'll get to the low-ranked part and the technical details when we get to that topic. Okay. Yeah. So yeah, it's a lot of stuff. So a lot of things happen to get to a final API. Okay, so let's go back to basics. What is a language model? Like, how do you define a language model, right? So one definition is that they're scientific data-driven models that help machines understand language and patterns in sentence construction. This for language. For videos and images, you can use the analogous data. So understand language and patterns. So it's really, one of the earliest language models were called stochastic parrots, because they're parrots because they repeat stuff they've seen before, but they're stochastic because you don't know what they're going to repeat. But they're going to regurgitate what was said before by someone. And they were really primitive, the ones. But right now what we have is like a much more than a stochastic parrot, because it can also do reasoning and stuff. But it is still something that uses language and patterns it has seen before to do sentence construction. I mean, we do as well. Like, if you look at how do humans, as humans, how do we construct sentences? How do we understand language? There are neurons in our brain that are dedicated to language and vision and memory and different things. So they get trained every time we have a new experience or a conversation, or every time we spend some time talking, or we learn a new language, new neurons get formed and fired in the brain, right? So even we are data-driven, to be precise. Our human brains are data-driven. So it totally makes sense. So language model, in a basic level, is if I have a word, what's the next word after this? If I have a character, what's the next character that's going to come after this? So that was the original premise of a language model. People were actually predicting just characters in the beginning, not even words. So we had character level AI model. It was just predicting the next character. If you say, okay, SEATTL, what's the next character? What's the next character? E, right? Because that's Seattle, right? Very likely. But you could have next characters that could be different, right? If I say BA, what's the next character?
Lots of possibilities.
Lots of possibilities. So that's where the stochasticity comes in, right? So simple models would just look at, okay, I just know BA, what's the next character? It could be anything, so you spit out something random. Or you spit out something with some probability. You see this more often, so you spit that out. But then the models evolved and they said, okay, can we take some context from the previous sentence, maybe, and then see if I can, make a better prediction, right? So something like, I just got promoted, I am feeling so. What do you say? Happy. Yeah. So that's, you could have said joyful, you could have said amazing, but happy seems like the most probable word that you would say, right? Yeah. I just checked my application status and it got blank. It's so frustrating. What would you say? Sorry? Denied. Yeah, denied, rejected, one of those. Yeah. So if you look at these two, right, how did I predict happy? Because I looked at the sentence, I just got promoted, and that conveys some sentiment, that has some inherent sentiment. So I capture that sentiment, I keep track of it, and when I get to I'm feeling so, you say, oh, well, that sentiment must be positive, right? So you're using information from the previous sentence to actually inform you on the sentiment here, and then you make a prediction. So these are encoded as latent state variables in the models, right? And then the state captures that there is some emotion involved, and the emotion is positive, and then it just responds accordingly. So if you look at this one, if I had to fill in the blank, was it just enough to look at the previous sentence? No. I had to do time travel. I had to look into the future, not just the past, right? Because I have no way of saying if it got rejected or it got accepted, right? Until I know what's coming up next. So this is where models have to look at the past and also the future when they do the training to understand how to make a prediction. Yeah? For training. For inference, you don't know what's coming up anyway. But for training, you'll have to do that. Okay. And this is something that when we get to this, we'll talk about it. This is what differentiates transformer models from its predecessors, which could not really do this looking into the future as well, right? So we'll talk about it when we get to transformers. Okay. So LLM, so now we add a second L, large language model. So LLMs are language models that are learned from massive corpuses of text that are mined from the web. They're known to be sophisticated in understanding language and can be generative in nature, right? So they're large. How large? We'll come to large in a bit. We'll cover that as well. So let's look at a history of language models a bit. How did machines work with language before and how do we have it now? So we'll look at some history in today's lecture, right? So one of the first models is something called perceptron. So if you look at the figure on the bottom, I think it's a little bit tiny font, but you can see neurons and you can see an operation, sigma operation, and then there is a summation, and then there's a sigmoid activation function. The ones on the left are the neurons, and the neurons, there's something that happens with the neurons and there's an output, right? So if you look at the figure at the top, that's an actual depiction of a neuron, right? A single cell neuron. It has dendrites and axons. It takes in information through, I think, the dendrites. Yes, it takes in information through the dendrites, and then it does something within the cell. There is some magic that happens within the cell, some chemical reaction, electrical impulse. Something is happening to the information which is coming in as electrical and chemical signals. They're getting transmuted, and then it gets passed on to the next neuron, and it gets passed on to the next neuron, and it happens billions of times. So every time we speak or we do something sophisticated, billions of neurons are actually firing in our brain right now. I don't know how many are firing right now for me, but also for you, for all of us, right? So that's it's really incredible. Like we are a neural network, so we are a natural neural network if you just look at the brain. And the one below is an artificial neural network. So ANNs were modeled after what we see in the brain, right? So this is the technical term for this is perceptron. So a single cell neuron, if you can use it to make a prediction, then you would say that's a perceptron. What's the practical implementation of perceptron called? If you might have seen it in a previous class. How do we actually use perceptron? It's a model. It's a model you're familiar with if you've taken a machine learning course. No, it's simpler than that. Sorry? Yeah, one step before that. So perceptron is like the theoretical construct, but to make it practical into an algorithm, you need a model. So it takes that theoretical construct and makes it a model. Sorry? Logistic regression, yes. So if you look at the perceptron, it actually has a step function instead of a sigmoid. And then logistic regression turns it into a sigmoid. So sigmoid makes it practical. Step function is not very practical because it's not differentiable. So mathematically, you need to change a step function to a sigmoid, and that changes perceptron to logistic regression. So logistic regression is the implementation of the single cell neuron equivalent with the artificial neural network, right? And then came the multi-layer perceptron, which is what someone mentioned. And then the equivalent of that is feed-forward neural network, right? So instead of having just one neuron, have a bunch of neurons and have them in layers and have them pass information from one layer to the next. So every layer takes in information from the previous layers, and you start with the input layer and you go to the output layer, and you also have a hidden layer. So you have a bunch of hidden layers. So when you have a few hidden layers, you call it a simple neural network. When you have lots of hidden layers, that's when it becomes a deep learning model. So deep learning is just making the network deeper, add more and more hidden layers, that becomes deep. Right? So perceptron and feed-forward neural network were good with discriminative tasks. Can you tell me if this image is one of a cat or one of a dog? Is it cat or dog? Just tell me. Or it's none of the two. Right? Simple tasks, discriminative. You just have to discriminate. You don't have to generate anything. You don't have to generate a sentence or a full, it's not generative in nature, right? Even with images, you can generate image, like you can say, hey, give me an image of a cat sipping something on an island, and you see these funny images of cats sipping some or playing it cool on an island, and it's generated, right? Discriminative version would be, can you describe what's in the image, or can you tag what's in the image? And I'd say, okay, that's a cat, there's an island, there's something. So that's discriminative, right? So if you have to move from discriminative to generative models, we need to be able to predict not just a class, but also the next token or the next word. So that's where the idea of recurrent neural networks came in. So RNNs, were the earliest idea of generating the next token. So as you can see here, we spoke about character level generation. You can see that this RNN is looking to predict one character at a time. So in this example, it's looking to predict jazz. So if you're given J, predict A, given A, predict A, given A, predict Z, but you kind of know what's come before as well. So this is just taking a feed-forward neural network and recursively going through it through layers, right? Until your generation is done. So that's why you see like a arrow coming back to the RNN model on the left, bottom left. That's saying there's a recurrence going on there. So RNNs were great, but they came with some drawbacks, with training, with not being accurate, with hallucinating. So hallucinations are not just something that LLMs had. It started with RNNs. So RNNs were one of the first models to start hallucinating, because now you're being generative, and it would even repeat words. You say, I love Seattle, and I want to tell you I love Seattle, I love Seattle. You just repeat that word 3 times, sentence 3 times, for no reason. And I would say no reason, but it's like, it's a training thing. It's how capable is the RNN to do the job that we care about. So there were hallucination issues, there were training issues, there was this vanishing gradient issue, if you remember, so that caused issues in training. So people said, okay, let's move on from RNN, let's go to LS. Okay, yeah, we have an example of RNN issue. So I just arrived in New York. In a few days, I would like to visit the city. What would be your guess? Or what would be your city? Just name a city. Sorry? Paris. Okay, yeah. So New York to Paris. Great. So RNN might just say New York, right? Because it likes New York. Doesn't make sense because you just visited New York. So how can you visit New York? I mean, what does it mean to visit New York again, right? Unless you went back, then you visit New York again. So that's where LSTMs came in. So LSTM refers to long short-term memory. It was said that RNNs had a very short-term memory. They couldn't really understand what happened one sentence or two sentences back. So they couldn't preserve context. Like we saw in that example where someone said, I just got promoted, so I feel happy. So that context is coming from I just got promoted. What if it came 2 or 3 sentences back, not just one sentence? Then RNNs would have issues with a short memory. It would just remember what happened like one sentence back. So the idea of LSTM was to increase the short-term memory, make it longer. So that's why the name long short-term memory networks, right? So they had like a cell state that was added in addition to the hidden state. You see, hidden state is called HT in this. H is the hidden state at timestamp t, and CT is the cell state, which is supposed to be a new state, latent state, that can preserve long-term information. It doesn't get crushed by gradient updates. It preserves information. It's additive in nature, whereas hidden states were multiplicative in nature. And the additive nature preserves things. Multiplicative things can make things vanish or destroy information. So LSTM was an innovation at that time. Even in 2019 or 20, I think I was at Meta and I was working on LSTMs. So the Transformers paper had come out, but we didn't have GPT up to speed. So people were still preferring other variants, maybe not LSTM, but they were looking at encoder-decoder models. And so GPT was not, we were not sure if GPT is going to work out or not. So we were still using LSTMs in 2019 and 20. So yeah, LSTM would be like, I just arrived in New York. In a few days, I would like to visit the city, Seattle, or whatever. A different city, not New York, right? So it would at least preserve the context from 1 or 2 sentences behind to respond. And fewer hallucinations, so not as much hallucinations, not so much repetition of the same word, same sentences. It was almost like, you know, you're dealing with a 1-year-old or a 2-year-old kid who would repeat the same things again and again. The brain is still evolving. So LSTMs were at that stage. RNNs and LSTMs were at that stage. Right? And then came attention. So attention is all you need is a very famous paper, very strongly cited, came out in 2017. But before transformer attention, there was LSTM attention as well. So attention, the idea of attention was already around with the LSTM networks. The idea is to pay specific attention to certain words. Given the context, you decide which words to pay attention to. Because, for example, if you say, I just visited the city, New York, I want to pay attention to New York because now I know you visited New York. So use New York, pay attention to it, and give me a different city, right? If I didn't pay attention, it's like someone's absent-minded, they're not paying attention. So the models could be like, if they're not paying attention, they're not accurate. So the idea of attention came in even with LSTMs, but it was taken to the next level with transformers, right? So that's LSTM with attention, did better than LSTMs. And then came the transformer model. So the figure on the right, this is from the famous paper, Attention is All You Need. It kind of encapsulates almost everything that we actually have as like the most basic architecture, right? It hasn't changed since 2017. People have just built on top of it, made it deeper, added more data, added more GPUs, done a lot of training. but the basic architecture is still the same. Maybe DeepSeek is looking to change it a bit. We saw something come up a few days back, but the one on the left is the encoding transformer, and the one on the right is the decoding transformer. So GPT just uses the one on the right, right? It doesn't have to use the encoding. It was thought in the beginning that you have to use encoding before you get to decoding, but then GPT said, okay, let's just use the decoding part. We don't have to worry about encoding. We'll just keep decoding. In encoding, you don't generate. You just encode, 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 and then maybe you discriminate, you classify, you make predictions, but you don't generate. With decoding, you actually keep generating. So the initial thought was you need to encode well before you decode well. But GPT changed the game by saying, we'll just focus on decoding. We'll do all the encoding within the GPT, don't worry about it. And then they made it work, right? So every version of GPT got better. And then now GPT is just use decoding component of the transformer. Okay. Yeah, so people still use the encoding transformer. So we still use encoding transformers in the industry, like BERT and variants of BERT, distal BERT, tiny BERT. The reason is that there are practical considerations when we actually deploy applications in production. One is obviously it has to be accurate. The second is that it has to have low latency. Again, depends on what low means. For some applications, you can meet with 1 or 2 second latency, then maybe use the most fancy LLM and maybe hopefully you can get it within 2 seconds. But for some applications, like you need instant results, or you need to be really quick, or you only have a small budget like 200 milliseconds or 300 milliseconds, or for search you only have like 10 milliseconds or 50 milliseconds, right? So when you're working with a budget, you really cannot use a more sophisticated, all-powerful model, right? So latency becomes a big factor in keeping smaller models and models from the past still in contention as as something you would deploy, right? So BERT is still used in the industry for a lot of classification tasks, and you can get really fast, really quick latency with BERT. So as long as your tasks are simple and not too complicated, and your accuracy needs are reasonable, you can get the job done with BERT. Obviously, if you used LLM for the same task, like Gemini or GPT, they would do better most of the time. Unless you really have fine-tuned it, they would do better or equal. But the reason is you have to be practical. You don't have that much, and the cost is another reason, right? So if you're handling tons of traffic and you're spending a lot of money on API calls, even with industry pricing or industry tiers, it can be like 2x or 3x or 5x or 10x more expensive to use an out-of-the-box LLM API for your production needs, right? When you can actually fine-tune smaller models on your own. Or you might have device constraints, like some companies might want to do edge prediction. So on the device prediction, you don't have resources, you don't have that much compute, so you have to be efficient, and you have to be memory efficient and compute efficient. That's another reason to consider these models. But anyway, so BERT is still used, and BERT is based on the architecture on the left, the encoding transformer. So that's and BERT is literally bidirectional encoding autoregressive transformer. Sorry, bidirectional encoding transformer. Yeah, so that's what it is. So yeah, I think some applications for BERT are like sentiment analysis, predict a sentiment, tag a review. Even it has done some, this used to be something that people cared about in the past, but if you want to summarize some articles, but you want to extract specific passages from the article, and you're not actually changing it, you're just like sharing specific sentences and then putting it together. That's called extractive summarization. Whereas abstractive is like you actually paraphrase it, reword it, share it in your own words, like GPT would do. That's abstractive. So for extractive tasks, BERT is still useful. Okay. Any questions so far on this slide? Okay, so you can see the evolution going from perceptron to feed-forward neural network, recurrent neural networks, LSTM, long short-term memory networks, LSTM with attention, transformers, BERT, and obviously GPT as well. So while BERT is purely about encoding and is called an encoding transformer, GPT is purely a decoder and is called a decoding transformer. Right? So we started with GPT, then GPT-2, 2.5, 3, and 3.5, and so on. Right? I think until 2 or 2.5 it was open source, so you could actually see what's happening. After that, OpenAI, made it closed, so you don't actually know what's the internals of what the model weights are. We kind of understand what the architecture is, but we don't know the internals or exactly how it's set up after GPT-3 or GPT 3.5. Right? Yeah, and all these decoding transformers are trained on next token prediction. So just predict the next token, next word. And they do a really good job. And even if they went, you remember in the last class we looked at an example where we had 3 ants walking in a line, and then the first ant said that there are 2 ants behind me, and the second said there are 2 behind me. So, and it came up with creative solutions, and one of the solutions, it was like, I think this is the reason why. And then, and it said that, and it went down that path and said, oh wait, it doesn't work. So, because it's generative in nature, it will keep going, but it can maybe reason or correct or, backtrack, right? But you're still predicting the next token. Like even if you're reasoning, even if you have to backtrack, you're still predicting the next token. So that's why, these days, this is another thought. I think with DeepSeek, we saw this, is they have a thinking mode within the output that they generate. So that's just pure thinking. It's just thinking. It's just the dumping its thoughts. It's like when you talk or you want to solve a problem, you dump your thoughts first on a whiteboard or with a friend. You're brainstorming. You just dump your thoughts and then say, okay, now that you've dumped all the thoughts, that's the thinking part. This is my final solution, right? So with DeepSeek, they actually trained it in that way that it generates the thinking part first, followed by the actual response, which makes it easy. Now you can just pick out everything outside the thinking part. But the thinking part is something it needs to do because it's doing it one token at a time, right? So it needs to go through all of that, and then we can extract the actual response.
Sorry, quick question.
Yeah.
If it's purely just generating the next token, how is it saying that it's reached a dead end?
How does it find that?
That it's reached a dead end, like can't generate the next token, or what?
No, it's analyzing whatever is generated so far. So everything that's it's generating or generated or is generating is used as input for the next token. So if I dump something for 2 minutes, I can look at the entire thing I said in the past 2 minutes and say, oh wait, now analyzing that, I think I have to backtrack or it doesn't make sense. So it's not just using this token to predict the next token. It's using all of what I've generated so far to predict the next token. And talking about tokens, I think this is a little bit outdated, but some of the large language models have at least 1 trillion tokens that they are trained on. So we're talking about data. So how many tokens? Token is, we'll talk about tokens when we get to the technical detail of it. We'll talk about when you get to transformers, but token is just like an equivalent of a word or half a word or a grouping of words that represent something useful for the LLM to work with, right? It can be a patch of words as well. It can be, whatever, a root of a word. It could be different kinds of concepts there, but something that is also generated ahead of time based on the data that a model sees. Say, okay, these tokens make more sense. These tokens will get used a lot, so let's use it. And so it has to go through 1 trillion tokens in training some of the large language models to actually do their training, right? So if we equate tokens to words and then words to books, how many books is 1 trillion tokens? How many words per book? Typical, let's say a 250-page book. Sorry? 25,000, 50,000. Let's say even had 50,000 tokens, right? We're actually looking at a data equivalent of having gone through 15 million books. So essentially, you're saying, hey, let's crawl the web, let's extract all kinds of documents, and I train with data that has 1 trillion tokens, which is essentially an LLM in a span of 1 month or 2 months, having gone through 15 million book equivalent data to actually do the training. So large actually refers to this. So when you talk about large, it's about how much data, not just the number of parameters. Even the parameters is huge, right? So we have 10 billion, 100 billion, 400 billion parameters. But even the tokens, the amount of data it's trained on, it's massive. Okay, so that's what makes it large, is the architecture and also the data that you're actually going through to train these models. So this is the thing, we don't go through 15 million books in the fine-tuning part, or in the in LoRa fine-tuning or Instruct fine-tuning or RLHF. It's much fewer, like equivalent of maybe thousands of books or something like that, right? So that's why it's a foundation. The foundation is very, very strong because it's based on so much of data. It's seen so much of data that it's such a strong foundation model. Okay. Any questions so far?
Does the amount of tokens is the only determining factor of the quality of the LLM?
So it has been shown that having high quality foundation data, like for the pre-trained model, and also for Instruct fine-tuning is super important to get higher accuracy. So there was an experiment that was done by one of the researchers from Microsoft. They took a large model, say Llama 3 or GPT or whatever, and they generated high quality textbook data. They generated textbooks. They said create a textbook, but it has the structure and it has to be of this quality and everything. And they used that to train a smaller model, which is I think called Phi. So Phi 1, Phi 2, Phi 3. And then it did better than other small models in the same category. So you measure the category by the number of parameters that the model has. So I think Phi had between 500 million to 1 billion parameters. So on 1 billion scale, using high quality data, which you can, because if you go and look for Reddit data, there'll be a bunch of good and bad stuff, right? So you'll have to have filters through that to filter out data and say, I don't want to use this for training, I want to use this for training, and so on. But once you have a fine-tuned model that has some safeguards, then it's going to generate good data. So you can use a large model. That's like a teacher is training a student, which is a smaller model, by supplying it high quality data. It's fabricated data, but it's high quality. But it's based on real data. And then that does better than other models in the same range. So that's something that they showed sometime back. But even for large models, like a lot of teams that do pre-training and post-training, they invest a lot on high quality data and measuring what are the data sources and how do you know your data is actually of high quality. There's a whole amount of money and energy invested just in data. And there are people who get paid quite a bit for just generating high quality data, right? So data is gold. Data is very, very important. So okay. So this is taken from a paper from some time back. I just referenced it again. It's a little bit old, but the idea is that we're going to focus a lot on natural language processing and natural language processing use cases for LLMs. So we'll be using this as a repetitive context for us to talk about the course content, right? So one of the table on the left, the table 1, you can see that they did some research on how what's the distribution of use cases of the API for Instruct GPT. So this is a Instruct GPT version. And they said that there's generation, open Q&A, brainstorming, chat, rewrite. So rewrite is, here's a sentence, here's an email, rewrite it, make it more, here's an article, make it more polished. Summarization, can you summarize this whole text for me, right? Classification, we spoke about it. You can tag it with sentiments, or you can tag it with topics or categories. So yeah, this is kind of the distribution that they found there. But there's many more applications, many more that we'll probably discuss as well. Are we okay going till 6:30 today? Does anyone need a break? 5-minute break? I want you guys to be awake in the next 1 hour. So if it helps to have a break, okay, you need. Okay, so see, you need to be like him. What's your name? So he's like, hey, I'll be the first, because now after he goes, everyone will join him. I know that. So we'll take a 5-minute break. Okay. See, a lot of people are going now. You don't want to be the first to raise your hand, but you do want to go. So we'll form groups of 3 or 4. So not 2 people, maybe 3 or 4 people. And again, sit with someone you have not sat with before. I know you might want to sit with your favorite people, but this is a way to get to know more new folks, right? We have such a big class. So sit with someone new, 3 or 4 people, and we'll talk about some business applications or pet projects that you are looking at right now, or you want to look at, or you have a project in the company you work at, and you just want to kind of do a sounding board or a brainstorm on that, right? For example, and also pick a company, like if you have your own company, great. You have problems in your own company, great. Or pick a company, let's say Amazon or Instacart or Walmart or eBay, and actually go to their website, right? Go to their website, and we'll keep this product focused. So look at their product features, right? What are some products that they have to offer? Like, products is not just like actual products. It can also be a feature on the page, right? And use that as a context and see how can LLMs help here, or will they help or will they not help? Is this like a straightforward thing, or is this something they have to figure out, right? So play around with that, and maybe you can play around with that for a few minutes, and then you can discuss as a group as well. So this is a good way for you to like get into thinking about, okay, LLMs and applying them in a practical setting. Okay. So definitely discuss if LLMs would be good to have. Is it a good to have, or it's actually really needed? You cannot do without it, right? For example, we saw one example, last class. We said if you have the Amazon page, and then there is the customers say, there's a summary of reviews for a particular product page. That has to be done through a generative AI model, right? There's no going around it. Whereas if you look at different categories that are available on the product line at Amazon, it might be something that's generated manually, or it's been over the years, or it might have a mix of some AI generated categories as well. So that's another example. So just maybe get into groups of 3 or 4, and I know once you start talking, it'll take some time. So, but I think it's, do you guys think this is helpful to do? In addition to just concepts and intellectual understanding? Yeah? Okay, so we'll use the next 15 minutes or so, probably till end of class. just find 3 or 4 new people. Maybe you want to get up and then walk around, say hi, and definitely say hi. Don't rush into the discussion. And then, and if you have any questions, I'll be here, and we'll wrap up after that.